Thank you very much for this introduction, and thank you very much for inviting me. It's a pleasure to share with you our experience. I don't know if you can see my screen.
Yes, you
yes.
can. Yes, not in presentation view, full screen yet, but yes, we see it.
Okay, then in presentation view.
Okay. Hold on. We are seeing the presenter view with the notes. You wanna just go back and put it on full screen.
So
I still
don't see the good.
Take your time.
I don't know what you see. What do you see, in fact?
We see both slides with the note view, basically, the presenter view, not the full screen. Okay, now we're good.
Okay, good. Sorry for that. So what I would like to share with you today is to explain first what are the main challenges of historic concrete conservation, and then I will end with a series of demonstration sites. So first, I would like to show you that from cement to reinforcement, we have a wide variety of materials. And just a few examples, I don't have time to go into details, but to show you where the cement were used and what was the type of cement that were used. And the story began in the end of the 18th century with Smeaton, as you can see his lighthouse here. And then we have French cement in the north of France from the early 19th century, and then a lot of different typologies of cements in the natural cements in the 19th century. And then by the beginning of the 20th one, we have the slag cement that did appear, then fly ash, silica fumes, to nowadays ternary binders that we are going to find in the repairs. Another point is that we have a great diversity of reinforcement. For example, here on Troyes Cathedral in France, in the center of France, we in the 19th century, bones were used to reinforce concrete. Then rebars. Another example of another cathedral in the 19th century, all the ochre parts are natural cement repairs on this stone cathedral, and as you can see, they were reinforced with rebars. Then we also have such type of rebars. Here we are in Chapelle Notre-Dame-du-Haut in Ronchamp from Le Corbusier, and you can see that it's a network of rebars, really unusual. We've got the standard ones and a grid. And then we have the fibers that we can find in museum, for example, in Marseille. Then we have a wide diversity of shapes and innovation. The concrete has been a vector of technical, architectural, and artistic creation. Here you've got the example of one of the first bridges in Châtellerault in 1900, and it was a 150-meter wide, long, 8-meter wide with 3 arches. It is one of the first ones. Then here you got an example of use of concrete as a repairing material after war. Here it's the Reims Cathedral in the eastern part of France, and you can see that all the structure made of wood has been replaced by a structure made of precast elements of concrete. Then a lot of things have been tested with concrete. It really was a vector of creation. Here, for example, you've got the market hall of Reims, which is very thin. If you can see the mouse, you can see here the size of a man, so that it's a huge vault, which is only 7 centimeters thick. We've got also a lot of examples of really unusual designs. Here it's the flower houses. It's in the forest, and a lot also of sculptures. Those are made with sprayed concrete. We also have a lot of elements from the gardens of the 19th century with concrete imitating wood. We also have very unusual sculptures. Here, the name is Cyclope, and it's nearby Paris, and it's a sprayed concrete covered with mirrors. And of course, a lot of vaults mixing concrete and glass. And also a lot of it's not stained glass windows, it's windows which are using concrete to replace lead. So here it's dalle de verre, and here we are in Royan. It's 3D shaped windows. As you can see, there is glass perpendicular to the joints also. And here it's a very beautiful one. It's a crystal paste, and all what you see in dark is not at all lead, it's cement paste. We also have a wide diversity of pathologies. Due to those specific rebars, I've shown you the Camille d'Or bridge, and here you can see the staples, the specific staples of Hennebic. It's a specific system to link the rebars, and we can see that we had heavy corrosion with those metallic reinforcements. We also have the Cotensin system, where you got the rebars that are in the bricks and which are filled with cement, and you can see the result of the corrosion of the rebars, which is quite a problem to restore. And then the flower house we've seen earlier, you can see here pictures from the construction, and here the decays that we have nowadays. We also have surely intrinsic low concrete cover for such a sculpture. You can't have the necessary concrete cover, and you can see that on this tower, which is hall, and here on Kissaring in Necker Hospital in Paris, fresco. So heavy corrosion, and here I've shown you've seen already windows mixing glass and concretes, and unfortunately there is reinforcement, and the size, the thickness of those pieces are the thickness of the glass pieces, so that the concrete cover is not enough. And you've seen also Freycinet marketplace. This is another Freycinet place, and again the vault is 5 to 6 centimeters thick, so that the concrete cover is not enough, so that we have heavy corrosion. We also have chemical incompatibilities due to experimentation, and here is an example from the late 19th century, where natural cement was used for decoration ornaments, and Portland cement was used for the structure, and the mix of both cements, as here you can see the natural cement under the microscope, and here the Portland cement. You can see that the composition is really different, and the point is that in the natural cement we have a lot of sulfate, that have created sulfate reaction in the Portland cement. As you can see the cracks, and under the microscope you can see the Etringite needles formation. And we also have unusual composition here with Le Corbusier in Village Adret, where he used a mâche fer, which is a mix of slag and iron. And you can see that this mâche fer was used both in as a gravel, but also into the mix. And you can see that the result is all what is dark here is just hollow area, so that it's very porous concrete with, in addition, some spots of pure iron, which can corrode as the rebars. And for this specific building, Le Corbusier used mâche fer concrete. On the top of it, a render, and on top of it, a second render. And this second render, which was ochre colored, finally it appeared that it was gypsum. So that he used gypsum outdoors directly on the concrete, which is already today totally forbidden due to possible sulfate reaction. And that's exactly what has happened there. Another chemical incompatibilities. Here you can see an example of a house with mosaics that was built nearby the sea. And the pieces of the mosaics were pieces of glass, of plates, or whatever the artist could find. And so there you can see that he used a sand containing shells, but also containing chloride, so that the rebars corroded very, very actively. And the other point is that he used cements containing a lot of alkali, and we had alkali aggregate reaction, and you can see that the strength of the reaction that has completely cut some of the aggregates. So the associated challenges are first, how to measure corrosion, how to perform a corrosion diagnosis with those erratic rebars. The second one is how to design restoration treatment. And one of the challenges is, can we, as for any other historical monuments, according to the deontological rules of conservation, can we conserve the initial design when we have incompatibilities? That's what I'm going to try to show you, how to cope with those challenges, and showing you some examples of repair operation that we've followed up. And I'm going to show you a series of case studies with patch repairs first. So I'm going to show you first Jaoul houses. It's a repair with like-for-like concrete in 2022. Then the Le Raincy Bell Tower. It's a church, very well known, again with repair with like-for-like concrete in 2022. And Iéna Palace with repair with like-for-like concrete in 2014. So first, the Jaoul houses. The construction period of the houses is between 1953 and 1955. They are located nearby Paris in Neuilly-sur-Seine, and the architect is Le Corbusier. And we have two houses because it was two families that were brother and sister that were living there. So there was a first repair period in 1991, and the repair strategy at that moment was to realize a custom concrete with a wooden formwork prints, and pressure water was used to remove superficial cement paste after initial setting. And it was quite well preserved. We've got almost 30 years of durability of those repairs. You can see here some of the repairs after 30 years that were quite in good shape. Nevertheless, what we found is that, dealing with diagnosis, the diagnosis was performed in 2018. We had deep carbonation of the concrete. As you can see, depending on the facade, it could go to 35 millimeter, which is quite high. And here you can see the amount of rebars in carbonated areas in the first house, and it could lie between 0 to 100%. On the second house, same range of carbonation thickness, and a little less areas where the rebars were in carbonated concrete. What we also try to analyze the type of cement, the type of aggregate, the cement content, and first we could see that we had quite high porosities with a quite high water to cement content in the original concrete, and low chloride content, low alkali content, and quite high sulfate content. And for the repair mortar that were used, we had a slag cement that was used, limestone and silicate aggregate, which was a little distinct from the original one, quite high porosity of the repair mortar, and lower water to cement ratio than the original one. As some observation have evidenced porous microstructure with medium to low cohesion, with no crystallization or pathogenic phases, with only a few gypsum crystals that you can see here on the microscope. That was for the original concrete. And for the repairing mortar, we had microporous microstructure, good general cohesion, but cracks between the cement base and the aggregates, air bubbles, and gypsum crystals near the surface. So the repair was operated by Claudia Deveau, who is a heritage architect, and she performed mapping of the original patches for each facade of the two houses. And what we could see that 72% of the total material elimination were from the repairs of the 1991, and so that it showed that even if visually the repairs seemed quite okay, in fact there were issues of bonding and so on, so that we had to eliminate quite a lot of concrete. So the conclusion of the diagnosis was that the main issues for the original concrete was the carbonation-induced corrosion. And I would like to mention there that this work of feedback on durability of patches was performed within the frame of an international cooperation project, which name is PEPS. It's a cooperation between the US with the Getty Conservation Institute, Historic England, and France LRMH. And the idea is to evaluate the durability of patches and to compare the practices between the three countries. So there, the evaluation of the patches showed that we had a wide range of quality of the patches between good to bad. We had very poor performances of the repair mortar, which were lower than that of the concrete. We've seen that, more porous, very poor bond, strong carbonation, and we had repair implementation defaults. As you can see here, the rebars were not cleaned on their total circumference. And we had passivation treatment that was applied both on the rebars and on the mortar, which is forbidden. But we had an almost perfect aesthetic match and quite good durability in spite of non-conforming implementation. So the restoration work was performed by the company Neuf Béton, and the repair strategy was to perform like-for-like mortar with an in-situ mix design The passivation treatment was applied only when the concrete cover was lower than 3 centimeters, and again, wooden formwork were applied. And here you can see the concrete removal and the rebars cleaning. And you can see that the initial prints of the wooden formwork was preserved. Here you can see the formworks, the wooden formworks, and here the results. And the final appearance is that it's almost invisible. Here is the repair. Here again, the repair. Now let's move to Raincy Church and its bell tower. So the bell tower was built by the brothers Auguste and Gustave Perret, and from April 2022 to April 2023. So it's a very short period of time to build this church. The materials used were reinforced concrete, and we had facade fillings with concrete slabs with a decorative exterior pattern of claustra, square shaped or round shapes. And the environment is urban and with oceanic climates. We had previous repairs on this bell tower, first in the 60s, and then in the 90s, and another one, and the second one in the 90s, early 90s, and then from 95 to 2018, regular purges due to spalling, without additional repairs. And if we come back to the repairs of 1991, again part of the PEPS project, we can see that again the passivation treatment was applied not only on the rebars but also sometimes on the initial concrete. We had a bonding primer that you can see here, and custom concrete with a slag cement based, and it was cast with elastomer coated wooden forms, and some of the repairs, as you can see, were bush hammered. I have to say that there was a realkalization trial in 2007, and we performed firstly some standard realkalization, and it appeared impossible due to the presence of aggregates which were reactive to versus alkali, and so that realkalization was not impossible due to possible side effects. Deleterious side effects. And so there was a realkalization trial with only hydrolysis. And as you can see here, the results were very insufficient. We only could realkalize a very thin layer around the rebar, and so that it couldn't be applied. So the diagnosis in 2019 and 2020 showed some biological covering, as you can see here, superficial erosion, as you can see here, corrosion of the reinforcing bars, cracks, swelling and spalling. And we had heavy damages in the beams, mullion and pillars. The identification of the concrete, the initial concrete, was that it was a mix of SEM1 with a quite high amount of cement, with quite high water to cement ratio, quite high porosity too, as you can see here, and nevertheless quite good compressive strengths. We had so that we have average compactness and quite good mechanical performances. And dealing with carbonation and rebars, what we can see that the carbonation depth was ranging between 9 to 19, so not that much finally. And we had from 0 even to 33% of the rebars in carbonated concrete. Then we could find that we had almost no chloride. We had a clear exogenous pollution of sulfates, sometimes higher than the 4% deleterious threshold, as you can see here on the mullion. And we could see also from the STEM observation that we had quite microporous cement matrix. The binder to aggregate contacts were ranging from dense to microporous, and we had some ettringite, but the primary one. And on the mullions, same, but secondary ettringite, in accordance with the sulfate content measure in the mullions, as you can see, we've seen. Yeah. So the conclusion that we had, the main issues was that we had carbonation-induced corrosion and the conclusion of the PEPS project that only 2% of the spalling area were from the 1991 repairs. And what we found is that the repair material was less porous than the original one, more rigid than the original one. Here you can see the dynamics modulus of elasticity of the original concrete and that of the repair material, so much higher. And you had few pathologies in the patches. The main degraded areas were in the original concrete at the interface with the repair, with a few corrosion area. And what we suspect is that it has not to do with the incipient anode mechanism, but more with the mechanical differences, mechanical performance differences between the patch and the original concrete. So good overall durability of the patch repairs of the 30 years, and the probable causes of failure: excessive patch rigidity, corrosion restarted in correlation with low concrete covers, and sulfate reaction at the interface patch and original concrete. So the new restoration operation was performed in 2022 with the architects Lacoste, Julien, and Bauchet. The company that did the restoration is Neuf Béton, and the repair strategy was to clean the concrete with wet abrasive projection, to eliminate mechanically dedicated concrete, to prepare the rebars, this time only applied when the concrete cover was lower than 3 centimeters. And new patches were designed with a customized mortar and concrete. It was designed to be sulfate resistant, as we have seen some initial sulfate pollution, and low alkali content due to the aggregates of the original concrete that were containing some elements which were reactive to the alkali. And a mix of different binders was the original quarry identified, and stiffness and porosity were adapted to the original concrete, and care was taken to ensure the quality of the interface with a sufficient compaction. And wooden formwork, when possible, were applied, and floral finishing was used when it was too difficult to use formworks due to the shapes of the pillars. And there was a bit
Elisabeth?
Waterproofing applied on the top of the pillars. So here you can
Elisabeth?
see the. Yeah.
Could you please go back to the previous
Yes.
slide, because the audio went away? Perfect. Thank you. The audio sometimes now goes back and forth.
Yeah, I have one suggestion, if I can. Can you please disconnect any other devices from your Wi-Fi and maybe start again to explain, like Irene said, 2 or 3 slides before, because the audio was not so perfect. Thank you very much.
Okay. I'm sorry about that.
No problem.
From there?
Yes, let's do that.
Okay. So as I said, the new restoration operation was performed under the direction of Lacoste, Thiolin and Baucher as architects. The company involved was Neuf Béton, and the repair strategy was to clean the concrete with wet abrasive projection, to eliminate the concrete decades, to prepare properly this time the rebars, to apply a passivation product only when the concrete cover was lower than 3. And the new patch repair were custom designed, sulfate resistant, as we had seen that there was sulfate pollution on the concrete, low alkali content because the aggregates were reactive to alkali, and there was a mix of different binders to obtain the color and the texture similar to that of the original concrete. The aggregates was the same. Original quarry was identified. Stiffness and porosity were adapted to the original concrete, and care was taken to ensure the quality of the interfaces with sufficient compaction. And finally, wooden formwork were applied when possible, but trowel finishing had to be used when it was too difficult due to the complex shapes of the pillars. And finally, bituminous waterproofing was applied on the top of the pillars. So here you can see the concrete removal and the rebars cleaning. Here you can see the new patches applied with the custom mortar and concrete. So here in formworks, and you can see after demolding there and there. And you can see here the difference between wooden formwork and trowel finishing, a little less good. And finally, the bituminous waterproofing. Now let's come to Iéna Palace. It was built in 4 phases. The first one from 1937 to 1939. And the second one was the construction of the rotunda, which was delayed to due to the Second World War. And then the other wings were designed later by Paul Villemont, and the fourth wing by Gillet and Boucher. And we will only talk about these 2 first period of construction. So what we can say is that we had a quite initial good quality of the concrete in phase 1, as you can see, with a lot of details. But we had some decays, a few spalling areas, as you can see here, especially on the garden facade, few honeycombings, few cracks and leakage and black soiling due to the urban environment. But I didn't say that Iéna Palace is just in the city center of Paris. On phase 2, we had even more decays on the garden facade. As you can see here, we had numerous areas with spalling, honeycombing, cracks and leakage, and a lot of black dirt deposits. And we could see also that we had large spalling, especially on previously repaired areas. So dealing with diagnosis, what we found is that the carbonation was quite limited. The average was 2.5 centimeter, but it could go up to 7 centimeters in some area. We had a superficial exogenous chloride pollution and quite a high sulfate pollution due to the urban environment. It could be up to 11% by weight of cement. We had locally low concrete cover with 3.5 centimeters as an average. If we compare to the carbonation average, it's lower. The carbonation is lower. And we had localized honeycombing due to the rough wood form, but globally good quality of the concrete. So the conclusion were that we had the urban pollution with black soiling, sulfate and chloride, and carbonation-induced corrosion. So for the black soiling, for this work site, we did perform some comparative tests of cleanings. And for the carbonation-induced corrosion, we took into consideration the presence of the sulfate pollution and of this hammered finishing. So that the repair included a substrate preparation, dealing with concrete and rebars. For the repairing concrete, we used specific design mix. And to reproduce the hammering finishing, a specific planning had to be applied on this work site to hammer the repaired areas only after 30 days in order to let the concrete to set. And there was a final patina according to the archives. So here you can see the cleaning tests with a different type of cleaning. I don't have much time to go into the details of those repairs. We found that some of the techniques were not good at all because they left some residues in the porosity. Here are pictures of the surface after cleaning with the different cleaning techniques. For some of them, we even have some salts that appeared. And finally, the best results were obtained with warm water with low pressure and low pressure abrasive projection. Here you can see the repair under the work site. So the mechanical elimination of the concrete, here the wooden form preparation, then the pouring by hand in the formwork. Then you can see that the surface after demolding with another thickness on purpose. It was meant to be as it is, to be able to be bush hammered afterwards. So after 30 days, we can see here the bush hammering, and here the final appearance with the almost invisible repair. I can say that the repair is there. And here is before repair on the left, and on the right after repair, and the ochre patina that we found in the archive. And now let's come to complementary treatments. And I would like to show you the example of the villa IE 1027. And it was built between 1926 and 1937 by Eileen Gray and Jean Badovici in Roquebrune-Cap-Martin in the southeast of France. And as you can see, it's facing the sea, the Mediterranean Sea. And we have structural elements and floors which are made of concrete, with non-structural components more heterogeneous with bricks and so on. And it was partially rendered and totally covered with lime wash. As you can see, white finishing. There was a first rescue operation on this house because it was abandoned for several years and squatted. And it had the highest French listing level in 2000 that was set in emergency. We had water infiltration, ground movements, and rebars corrosion. In some part of the villa, the state of ruin was close. So the diagnosis performed in 2000 showed a mix of cements with quite high amounts, calcareous aggregates with siliceous sand, a poor quality of the concrete, up to 17% of porosity, and which was more surprising, very, very low compressive strengths, that are more to do with calcareous stone than with concrete. We had quite often low concrete cover and noticeable carbonation, generally carbonation higher than the concrete cover, a slight chloride and sulfate pollution, friedel salt and punctually etrangite, which are consistent with the chloride and sulfate pollution. And we had corrosion of the rebars, corrosion-induced carbonation with slight chloride pollution. So there was the first deep repair operation in 2000, and the repair strategy adopted was to apply some patches. A mineral migrating corrosion inhibitors was applied, and the lime wash as a finishing and the repairs foundation of the foundation. In 2016, what was evident is that we had again generalized cracking with mechanical and corrosion origins. We had scaling, especially in the patio, spalling, again in the patio mainly, new infiltration from the balconies. And so that two operations were planned. First, a maintenance one to deal with the infiltration. And the second one was a second diagnosis phase and to elaborate a new repair strategy as the first one failed. So what we could see in 2016 is that the carbonation had progressed quite a lot, from 20 millimeters to 70 millimeters. We had massive chloride pollution, up to a 2.14 by weight of cement, and you probably know that the threshold is 0.4 by weight of cement. We had massive alkali pollution, probably due to the application of the mineral migrating corrosion inhibitor. We also had massive sulfate pollution with the progression of this pollution between the two periods of diagnosis. It was up to 5% by weight of cement, with again deleterious threshold of 4% by weight of cement. And the corrosion was still clearly active. So the repair challenges there was that the standard patch repair and migrating corrosion inhibitor had a limited durability. As I said, it failed. The other point is that we knew that the chloride pollution was inevitably dynamic. We are on the seashore, and that limited the possibility of electrochemical chloride extraction, because it could only be a temporary solution as the pollution is dynamic. Waterproofing paint was impossible because we had recurrent infiltration problems, and the concrete was loaded with different salts. So the last durable option was cathodic protection, but it's quite invasive for a historic concrete, where we expect a maximum preservation of the original material. So that, as I said, the new repair strategy contains first maintenance operation to deal with the infiltration and foundation issues. The second one was to verify the actual corrosion dynamics of the reinforcement and to evaluate the possibility of implementing an ICCP on a high historic concrete context. So that we first performed, our lab performed, implemented a corrosion monitoring strategy, mixing instant non-destructive testing, the standard ones with potential mapping, resistivity, and polarization resistance measurement, as you can see here, with 4 series of measurements at each season. And then we also applied an experimental permanent monitoring for 1 year with in cooperation with the Spanish colleagues, with Carmen Andrade and with the Safecore company. And here you can see temperature and humidity sensors and corrosion sensors that were applied directly on the concrete. And there was also a weather station, and everything was linked to a data acquisition system. Because if I come back to the instant non-destructive testing, we perform the test only once every 4 months or 5 months. But we know that those measurements are strongly dependent on the temperature and humidity. So that with the monitoring, we could have some data every half an hour. And all of those data acquisition system was connected to the internet, so that we could collect the data from the desk from Paris. So 2 spots exhibiting more severe corrosion according to the non-destructive testing were monitored with the permanent monitoring system. So a beam here and the southern balcony. I have no time to go into the details of the results, but what I can show you here is just the results of the non-destructive testing on the beams. And here you can see the corrosion current that were measured on the beam on each season. And what we can see is that gradually we had an increase of the corrosion current, and it was very clearly linked to the appearing of some cracks on the beam due to the corrosion. The monitoring showed exactly the same. So the synthesis of the complementary diagnosis were that we had a propagation phase of the corrosion, which were associated to cracking ongoing in some parts of the villa. So the corrosion was still very active. So that we could implement the ICCP trial with the objective or to evaluate the ICCP efficiency for quite low but recurrent corrosion currents and dry conditions, to try to minimize the invasiveness of the implementation of this system, which is more implemented on bridges or on industrial buildings. And the trial was performed in cooperation with a masonry conservation company, Chaux et Sable, with a company specialized in ICCP, Fraissinet, and everything under the direction of the heritage architect Claudia Deveau, DDA company. So just a few words about ICCP if you're not familiar with that. The idea is to decrease the electrochemical potential of the rebars to a threshold value, which name is the protection potential, where the corrosion current becomes negligible. And the ICCP characteristic is to impress a small but continuous current. It's a permanent treatment which needs maintenance and monitoring. Here you can see the implementation of the trial. So it was designed by Fraissinet, and we were allowed to implement it on 1 square meter of a pillar and of the patio, as you can see here and here. So we had some embedded anodes, reference electrodes, and wires to the remote control system and access to the current. What we have seen during the implementation is that the corrosion of the rebars was confirmed, as you can see here. So here, the details of the implementation with lines sewn for the wires, drilling for the insertion of the anodes. And as I mentioned earlier with the challenges is that the rebars were not connected, so that we had to restore the electrical continuity. So here you can see the nodes that were implemented and coated with a specific load composition, and then the reference for electrode inserted and wired. Then all the cables were inserted in the same holes to minimize the impact of the implementation. And then there was the cooperation of the Chaux et Sable company on the concrete finishing with the formwork board impressions and the white finishing. And here it's after the ICCP implementation and the repair of Chaux et Sable. And the conclusion of the trials is that it was possible to miniaturize the implementation with an adaptation of the historic concrete conservation deontology. There were nevertheless some finishing issues, and it was a success to have a synergy between the masonry company and the ICCP company. And on the basis of the results of this experimentation, the scientific committee of the villa opted for an ICCP, but only on the structural element facing the sea, and the underside of the balconies, considering that the ICCP was still too invasive for the rest of the ceiling. And now I'm going to show you the final restoration work. So on the left, during the implementation, and afterwards, when it was finished. So invisible after the whole restoration. Again, before, well, during and after. Same during and after. And again, during and after. So to conclude, we can say that the corrosion diagnosis there demonstrated the aggressiveness of the combination of the carbonation and chloride pollution for the reinforcement, even at low humidity. And what we can say that we know already the limits of the punctual measurement of non-destructive testing. There is a clear need for more developments in the techniques of monitoring for the corrosion of the reinforcement of the concrete. And this project is one of the first examples of ICCP applied in the field of historical monument in France, but it opened the door to these techniques. And but it also evidenced the need to have actors that are involved in the repair with a surgical implementation and a cooperation with a specialist of finishing. What I can say is that there are new developments in our lab dealing with monitoring and a close follow-up of the efficiency of the installation in this villa. We can say that also we have new installations since here in Le Touquet, Hôtel de Ville. It's in north of France, nearby the sea. And there it's very specific because we use carbon fibers for the current and not wires, standard wires, because there was both a need for mechanical strengthening of the tower and repair corrosion with ICCP. So the ICCP was using carbon fibers. So to conclude, what I could say that we, as you have seen, we had a wide variety of cultural heritage with typologies and uses. Here you can see we have a boat, we have towers, we have sculptures with painted sculptures, and we also have windows. We have a wide variety of periods of construction. Here, for example, it's the La Casa Mor from late 19th century to the more recent siège de Journal L'Humanité in Saint-Denis in the late 80s, sorry. We had a wide variety of material and finishing, as you can see. And an increase here, what you can see, it's a survey that we did perform. And here you've got the amount of monument made of concrete listed in France versus time. And you can see that we have a strong increase of the protection of the 20th century and especially concrete monuments. And we have now more than 950 monuments, because the last figures are dating back to 2021. We have multiple pathologies, but also multiple environment, urban, seashore, rural. We have different type of climates, continental ones, but we also have islands, the French islands in the Caribbean areas, for example, with other issue with earthquakes, with also much higher temperature and humidity. And I would like to end with some statements of, I'm sorry I didn't have time to put it in English, but I will translate it for you. And I would like to express the words of some colleagues architects from a conference organized by the Le Corbusier Foundation. And for example, François Botton mentioned experimentation which are facing the limits of the possible. And Bernard Bauchet mentioned, yes, we can restore, but it's impossible to respect the initial constructive models when they are not good. So the challenges are, as I said, the variety, but also the compromise. Sometimes we can't make like for like, identical. Sometimes we have to paint to not lose. We have also to develop the know-how of the people that are implementing the repairs. We also have to progress in the diagnosis, and durability is a real challenge, as it's a challenge deontological, economical, and cultural one. And there is a need for dedicated research. So I'm sorry, I think I'm a little too long, and thank you for your attention.